Every solar panel on every rooftop in the world is an engineered bandgap device. The silicon is specifically chosen because its 1.1 electron-volt bandgap overlaps with the peak of the solar spectrum, allowing it to absorb the maximum possible fraction of incoming sunlight and convert it to electrical current. Engineers modify the bandgap by alloying silicon with germanium or using gallium arsenide instead to tune the absorption edge with exquisite precision. The entire multi-billion-dollar solar industry rests on the same physics that determines why your window is transparent. Lasers, light amplification by stimulated emission of radiation, work by engineering band gaps in semiconductors to produce coherent light emission at a specific frequency. The laser in your Blu-ray player, the laser that cuts steel in a factory, the laser that carries your phone call through a fiber optic cable. All of them are quantum bandgap devices. Light being absorbed and re-emitted, but in a controlled, synchronized way rather than the random re-emission of an ordinary transparent material. And MRI machines, those enormous magnets in hospital radiology departments that let doctors see inside your body without cutting it open, use radio frequency photons that interact with hydrogen nuclei in your tissue. Radio waves, like visible light, pass through the body not because there are gaps to sneak through, but because the electron transitions in biological tissue don't match radio frequency photon energies. Your body is, to radio waves, essentially transparent for the same bandgap reason that glass is transparent to visible light. The MRI exploits that transparency to see inside you. The transparency of glass is not just the property of one material. It is a template for understanding how all electromagnetic radiation interacts with all matter, from X-rays through bone to radio waves through walls to visible light through glass. Every transparent material has its energy gap, its frequency window, its quantum lottery. Understanding glass means understanding all of it. Let me tell you what I find most remarkable about all of this. You have looked through windows your entire life. On your first morning in a new house, you walked to the window and looked out. On cold mornings, you press your fingertip against the cold glass and wash your breath fog against it. On rainy days, you watched droplets race each other down the pane. And through all of it, the glass was doing something that took the greatest physicists 300 years to explain, something that involves quantum probability, electron band gaps, the interference of probability amplitudes, the collective synchronized re-emission of light by trillions of atoms, and a fundamental irreducible randomness in which individual photons go through and which ones bounce back. The sunlight warming your shoulder right now through a window is made of photons that each individually won a 96% quantum lottery at the surface of the glass. The photons reflected back never reached you. They went back outside to illuminate the clouds or the street or whatever happens to be in the mirror image you see when you look at the window at the right angle. Those reflected photons weren't different from the ones that came through. They were identical. The glass didn't sort them by color, by energy, by age, or by any property you can measure. It assigned each one a quantum probability, and each one drew its fate from the quantum lottery with an outcome that was not determined until the moment it happened. Suppose you sat in a room and counted every photon that came through your window on a sunny afternoon. You'd count somewhere around 10 to the 22nd power, 100 billion trillion photons every second. Each one arrived because it happened to be in the transmitting 96%. If the laws of quantum mechanics had set that probability slightly differently, if the band gap of silicon dioxide were 2 electron volts instead of 9, none of them would make it through. Your room would be dark. Every room would be dark. Not because the sun stopped shining, but because the particular quantum mechanical arithmetic of silicon and oxygen bonding would have turned every window in history into a wall. Here is what I want you to take away from this. The transparency of glass is not an obvious fact about the world. It is a specific, numerical electron energy fact, a consequence of silicon dioxide having a band gap of approximately 9 electron volts, sitting comfortably above the 3.1 electron volt ceiling of visible light. It is, if you want to think about it this way, a fact about how the universe's atomic architecture has to be arranged for there to be windows and eyes that look through them, and minds that wonder why. Feynman said, near the end of his life, that he had gotten so much more pleasure from physics by not being satisfied with the shallow answer, by always asking what is really going on underneath. The window was always there. The sand was always there. The silicon and the oxygen were always fused in their particular geometry. But the question, why is this clear? Turns out to open a door into quantum mechanics, electron energy levels, probability amplitudes, and one of the deepest facts about how matter and light coexist in this universe. Your window doesn't let light in. It performs a quantum computation on every photon that touches it, consults the laws of electrodynamics, rolls the dice of probability that Feynman spent his career describing, and passes the winners through. 96% of the time. Now go look at it again, and this time really see it. The wave equations only give you probabilities. They tell you there's a 4% chance each photon is reflected. Not which photon. Any given photon has a 4% chance. You cannot predict which one. You cannot control which one. You cannot know, even in principle, whether the next photon will go through or bounce back. This is quantum mechanics in the most direct, uncomfortable sense. Nature generates genuine randomness at the individual photon level, and the best physics can offer you is a probability. Now let me give you the result that really disturbed the physicists. Suppose you have two glass surfaces, the front and back face of a pane of glass. You might think, for percent reflected at the front, for percent reflected at the back, total reflection is just 8%. But it isn't. The actual percentage of photons reflected from a pane of glass varies between 0% and 16%, depending on the thickness of the glass. 0 to 16. If the glass is a certain thickness, almost no photons are reflected. The glass becomes eerily transparent, almost a perfect transmitter. Add a fraction of a millimeter, and the reflection jumps to 16%. Add another fraction, and it drops back towards 0. The reflection oscillates sinusoidally with the thickness of the glass, cycling through its full range every half wavelength of light, about 250 nanometers or about 250 millionths of a millimeter. What on earth is happening? The photons reflected from the front surface and the photons reflected from the back surface are interfering with each other. Their quantum probability amplitudes add constructively or destructively, depending on the path length difference through the glass. If the thickness is just right, the probabilities of reflection cancel to nearly 0. If the thickness is wrong by a quarter wavelength, they reinforce to nearly 16%. The glass doesn't decide. It computes a quantum probability, and that probability depends on the thickness of the pane the photon is crossing through. Newton saw these interference rings. We call them Newton's rings today, and couldn't explain them. Feynman, in his book QED, The Strange Theory of Light and Matter, used them as the opening exhibit in his explanation of quantum electrodynamics, the most precisely tested physical theory ever constructed. Feynman described each photon as exploring all possible paths simultaneously, a concept called the path integral formulation, which Feynman himself developed. Each path contributes a probability amplitude, and the final probability is the sum of all those amplitudes, with phases that depend on path length. For glass, the photon simultaneously samples both the front surface reflection path and the back surface reflection path, and the interference between those amplitudes, those quantum arrows, as Feynman called them, determines the probability of what you detect. The photon is, in a deep sense, aware of the entire thickness of the glass it is crossing, even before it crosses it. Feynman himself admitted, with characteristic bluntness, that nobody knows how to visualize what this actually means physically. We just know that the calculation matches experiment with extraordinary precision. Let me make this viscerally concrete. Right now, sunlight is striking your window. Billions of photons per second hit the glass every square centimeter. Each one faces a quantum probability, 4% chance of reflection, 96% of transmission. They do not consult each other. They do not coordinate. Each one independently draws from the quantum lottery. Not because there's a mechanism determining the outcome, but because quantum mechanics says the outcome is fundamentally indeterminate until the moment of detection. The photons that reach your eye have won a probabilistic contest whose rules were written by Feynman diagrams and enforced by the geometry of space-time at the atomic scale. Now let me zoom out because this principle doesn't stop at your living room window. Every piece of glass in a telescope, including the 10-meter mirrors of the Keck Observatory in Hawaii, works by exploiting the same transparent yet reflective duality of glass surfaces, with precisely engineered coatings designed to tune those. Quantum reflection probabilities. Optical engineers calculate the exact thickness of thin film coatings to make reflection probabilities cancel to nearly zero across the visible spectrum, turning mirrors into transmitters or transmitters into perfect mirrors by manipulating the quantum interference of photons at surfaces nanometers thick. The multi-layer anti-reflection coatings on your eyeglass lenses, on your camera lens, on your computer screen, all of them are applied quantum probability engineering, layer by layer, each layer chosen to push reflection probabilities towards zero. Optical fiber, the glass thread that carries the internet across continents and under oceans, works because light can be trapped inside a glass core by total internal reflection. When light hits the glass-air interface at a sufficiently shallow angle, the quantum probability of transmission drops to zero and the probability of reflection becomes 1. Every photon bounces. The glass, which at normal angles transmits 96% of light, becomes at grazing angles a perfect mirror. 1 material, 2 behaviors. The angle determines the quantum probability. The Earth's atmosphere is, in effect, a selective window. Visible light passes through it almost perfectly. The atmosphere has a transmission window in the exact frequency range that our sun emits most intensely and that our eyes are tuned to detect. Ultraviolet light is blocked by ozone in the stratosphere. Infrared light is partially absorbed by water vapor and carbon dioxide. The atmosphere is a natural optical filter, transparent to what life needs and reflective to what would harm it. And the reason it's transparent to visible light is the same bandgap physics we discussed for glass. The molecules of nitrogen and oxygen in air have electron energy transitions that don't match visible light frequencies. The sky is clear because nitrogen and oxygen are, in the relevant quantum sense, blind to sunlight. And then consider this. Glass is transparent to visible light, but not to ultraviolet. Most ordinary window glass absorbs UV frequencies because the photons have enough energy, above 3.1 electron volts, to start exciting electron transitions in the glass structure. This is why you can't get a suntan through a window. The glass is selectively transparent, a frequency-specific quantum filter, and the cutoff wavelength depends on the precise chemical composition and band structure of the glass. Quartz glass has a wider transparency window, allowing UV to pass, which is why quartz is used in UV lamps and certain scientific instruments. The same principle, different band gap, different transparency range. The implications of understanding this correctly are not just academic. They are technological, medical, and civilizational. Now here's the crucial question. Why does glass re-emit the light forward, maintaining the image? Why doesn't it scatter the light in all directions, the way fog or frosted glass does? The answer is geometry and coherence. In a well-ordered, transparent material, the re-emissions from neighboring atoms are synchronized. They add up constructively in the forward direction and cancel in the sideways and backward directions through a process called interference. The whole crystal structure cooperates to maintain the original beam direction. It's like a disciplined relay race, not a crowd of people shouting in random directions. But this still doesn't answer the deepest question. Why do the electrons in glass cooperate with visible light at all, while the electrons in would refuse to? Why does cardboard absorb the light instead of re-emitting it? For that, we need to go one level deeper. Imagine every electron in a material as sitting in a room, and above it is a loft. The electron can jump up to the loft if it receives exactly the right amount of energy. Not just any amount, exactly the right amount. Too little energy, and the electron ignores the incoming light entirely. Too much, and it still ignores it. The energy has to match the jump, the way a key has to match a lock precisely. This is the quantum reality of electrons and solids. They don't exist in a smooth continuum of possible energies. They are confined to specific allowed energy bands, like rungs on a ladder with forbidden zones, energy gaps between them. A photon of light comes along and offers its energy to an electron. If that photon's energy matches the gap between the electron's current band and the next available band, the electron absorbs it, jumps up, and the photon is gone. If the photon's energy doesn't match any available transition, the electron ignores it. The photon passes by unreacted, as though the atom weren't even there. Now, visible light photons carry energies between about 1.8 and 3.1 electron volts. An electron volt is a tiny unit of energy, about 160 billion billionths of a joule, but it's exactly the right scale for atomic transitions in visible materials. And here is where the glass story becomes beautiful and specific. Silicon dioxide, the main ingredient of ordinary glass, has what physicists call a band gap of approximately 9 electron volts. That means the smallest energy jump an electron in glass can make requires 9 electron volts. The most energetic visible light photons carry only about 3.1 electron volts, 3 times too weak. They cannot excite a single electron in the glass. There is no available rung on the ladder at that height. The photons pass through the entire material, billions of atoms deep, without triggering a single lasting absorption event. The glass is, in effect, energetically invisible to visible light. Now consider pure silicon, the same element bonded differently with no oxygen. Silicon has a band gap of just 1.1 electron volts. Red light photons carry 1.8 electron volts. More than enough. Silicon eats visible light for breakfast, gobbling up every photon that hits it and converting it to heat or electrical current. This is exactly why silicon solar panels work, and exactly why the black chip in your laptop is completely opaque. Change the bonding, change the partner element, change the band gap, and you change whether the material sees the world or is blind to it. What is a more complex story, but the principle is the same. What contains organic molecules, cellulose, lignin, various pigments, whose electrons have energy transitions scattered throughout the visible spectrum. Some transitions absorb red, some absorb green, some absorb blue. The net result is that most visible light photons find at least one electron they can excite in wood. The light is swallowed, converted to thermal vibration, and never re-emitted coherently. The wood warms slightly. You see nothing through it. Glass, by a remarkable coincidence of chemistry, or a remarkable requirement of any universe capable of producing eyes and windows, has no available electron transitions in the visible range. The atoms of silicon dioxide are bonded with such strength, their electron clouds bound so tightly by the oxygen atoms, that the energy gap is enormous. Nearly 3 times too large for visible light to bridge. Not by chance, not by design, but by the specific quantum mechanical arithmetic of silicon and oxygen bonding. Suppose you could reach into a pane of glass and change the energy gap. Just reduce it from 9 electron volts to 2 electron volts. The glass would darken. Reduce it to 1.1 electron volts, like silicon, and the glass becomes as opaque as coal. The transparency of your window is not a generic property of solids. It is a specific, quantitative electron energy fact written in the atomic structure of silicon dioxide, expressible as a number. Mechanism, Layer 3. The quantum scandal Feynman uncovered. Now I want to tell you about a problem that bothered Isaac Newton and that Richard Feynman spent years developing the full answer to. And it is, in my view, the most scandalous and beautiful thing about glass that go back to that window. Look at it carefully. You said you can see through it, but you also said you can see your reflection. Let me put some numbers on that. Of all the photons of visible light that hit a clean glass surface at right angles, approximately 4% are reflected. Not absorbed, reflected. For in every 100 bounce straight back, 96 pass through. This seems perfectly reasonable on the surface. Glass reflects a little, transmits most. Fine, no problem. But here is the problem. Light is made of individual photons, quantum packets of energy. Each photon is identical to every other photon of the same frequency, and yet 4% are reflected and 96% are transmitted. The photons are indistinguishable from one another. So how does the glass decide which ones to reflect and which ones to transmit? Is there a tiny inspector at the surface checking photon ID cards and sending some back? Is there something different about the reflected photons that we're missing? Newton wrestled with this exact question in the 1600s. He called it the problem of fits of easy reflection and easy transmission, which is about as honest and confused a label as a genius has ever put on an unsolved problem. He couldn't explain it. He knew something was wrong with his particle theory of light. These fits suggested the particles had some kind of oscillatory property, but he couldn't crack it. He died with this mystery unresolved. The wave theory of light gave a partial explanation. The reflection and transmission percentages can be derived from the wave equations. They depend on the refractive index of the material and the angle of incidence. That's satisfying for beams of light. But for individual photons? Walk up to your nearest window. Right now, put your finger on the glass and look through it at whatever is on the other side. A street, a garden, a parking lot, it doesn't matter. You can see it clearly, as though the glass weren't even there. Now, tilt your head slightly and look at the glass itself. Not through it, but at it, and notice that you can also see a faint reflection of yourself staring back. Both things are happening at the same time. You're looking through the glass, and you're also looking at the glass. The glass is simultaneously transparent and reflective. And most people see this their entire lives and think absolutely nothing of it. I want to tell you that this is one of the strangest things in all of physics. Your window does not let light in. That's the first thing I need you to understand. Not in the way you imagine. Light does not slide through glass the way water slides through a pipe. It does not squeeze between the atoms the way air sneaks through a screen door. Something far more extraordinary and far more unsettling is happening every single time sunlight crosses your window pane. And understanding what it actually is will change the way you see every transparent surface you ever encounter for the rest of your life. Here is the paradox I want you to sit with. Glass is made of sand. Ordinary beach sand, melted and cooled. Sand is made of silicon and oxygen, the same silicon that is in a slightly different form, used to make the opaque black chips in your computer and your solar panels. Silicon in one arrangement is completely opaque, not even close to transparent. Silicon in another arrangement, bonded to two oxygen atoms in a particular crystalline geometry, becomes the clearest material human beings have ever engineered for windows. Same element, two arrangements. One blocks all light. One passes it almost perfectly. Why? The answer runs through quantum mechanics, electron energy levels, a Nobel Prize-winning physicist who spent years obsessing over this problem, and a deeply unsettling fact about probability at the atomic scale. And I promise you that by the end of this, you will realize that looking through a window isn't passive observation. It is the outcome of a quantum lottery that billions of particles win or lose every second, for reasons the greatest minds in physics took 3 centuries to understand. Look at a pane of window glass head-on in bright light. You see right through it. Look at it at an angle, against a dark background, and you see your own reflection. Both effects are real. Both are happening simultaneously to every photon of light that strikes the surface. Now here is what should bother you. Glass is solid. It is denser than air. It has more atoms per cubic centimeter than the air around it by a factor of roughly 1,000. If you try to push a marble through a box of marbles packed tightly together, it wouldn't get very far. And yet, visible light, which in vacuum travels at 299,792 kilometers per second, a speed so fast it could circle the Earth 7.5 times in a single second, sails through a centimeter of solid glass in about 50 trillionths a second, not slowed to a stop, not scattered into chaos. Transmitted almost perfectly, carrying with it a sharp image of the world outside your room. Meanwhile, hold up a sheet of cardboard. Same thickness as the glass. Put in front of the window. Total darkness. No light gets through. None. And the cardboard isn't made of something fundamentally exotic. It's made of wood fiber, which is mostly carbon, hydrogen, and oxygen, three of the most common elements in the universe. So why does light pass effortlessly through one arrangement of atoms and stop dead at another? The answer is not, as you might instinctively guess, that glass has bigger gaps between its atoms. It doesn't. The answer is quantum mechanical, and it goes right to the heart of how matter and light interact at the smallest scales. But before we get there, let me back up one step further. Because to understand why glass does what it does, you need to understand what light actually is. Not the hand-waving version. The real one-dot light is an electromagnetic wave. That's the classical picture, and it's still useful. An oscillating electric field and a magnetic field, perpendicular to each other and perpendicular to the direction of travel, rippling through space at 300,000 kilometers per second. Each color of visible light corresponds to a different frequency of that oscillation. Red light oscillates about 430 trillion times per second. Violet light oscillates about 750 trillion times per second. In between those two extremes lies the entire rainbow of colors your eyes can detect. Now, when this electromagnetic wave hits a glass surface, the oscillating electric field begins to push and pull on the charged particles inside the glass. Every material contains electrons, negatively charged particles bound to atoms, and electrons respond to electric fields. They get nudged. They oscillate. They become, in a sense, secondary antennas that receive the incoming electromagnetic signal and begin to broadcast their own. This is the crux of the whole story. Glass is not transparent because light passes between its atoms like a ghost walking through walls. Glass is transparent because the electrons in glass absorb the incoming light energy and re-emit it almost instantaneously. And critically, they re-emit it in the same direction the original light was traveling, with the same frequency, building up a new wave that continues forward through the material. The light that exits the far side of your window is not, in any strict sense, the same light that entered. It is a new electromagnetic wave, reconstructed from the collective response of trillions upon trillions of electrons in the glass, each contributing a tiny oscillating re-emission to the whole. Now, something remarkable happens in this process. There is a tiny delay between absorption and re-emission at each atom. It's infinitesimally small, on the order of femtoseconds, quadrillionths of a second, but it accumulates as the light passes through each successive layer of atoms. The net result is that the light appears to travel more slowly through the glass than it does through empty space. In standard window glass, with a refractive index of about 1.5, light travels at only about 200,000 kilometers per second, two-thirds of its vacuum speed. In diamond, whose refractive index is 2.4, light slows to roughly 125,000 kilometers per second, more than half its original speed, absorbed and re-emitted its way through one of the densest transparent materials on Earth. Think of it like sound traveling through a crowded hallway. The message gets passed from person to person. Each person hears it, turns, and repeats it to the next. The words arrive eventually, but the process of being received and retransmitted at each person introduces a small delay. The hallway doesn't stop the message. It slows it.